So then let me start. Welcome everybody. Nice to see many people here. So I hope you can hear me well. So welcome. We have only one presentation today, but a very interesting one. Florian Dignath, Dr. Florian Dignath, sorry, has been working at thyssenkrupp Transrapid for a very long time. I think he told me by email it's 22 years. Started when obviously, the Transrapid was running as the picture that he has in the background in Emsland at the test track in terms of Transrapid testing facility. It's been working mainly, from what I've understood, on the control side of the magnetic levitation, and has even supported TUM Hyperloop over the last years in developing our own levitation models, and in particular, the levitation model that we used in our test facility as well. So a lot of experience on the Transrapid as the overall system, but in particular on the control side of the magnetic levitation. So today he will share a little bit more of that knowledge of having worked on such a system, in particular system that is already running and working every day in Shanghai as well. So I think I have nothing to add to this. Thank you very much, Florian, for being here, and looking forward to your presentation.
Yeah. Thank you, Gabriel and Lucas, for the opportunity to talk about some of my experience from the last 20 years about with the Transrapid. In the beginning, I worked for some other parts of the Transrapid, but you're right, for the last 10 years maybe, I'm mainly busy with the control system and the general vehicle dynamics. Let me ask in this round, as control theory is a quite special topic, how much experience there's with control engineering at all in this round here. Maybe could everyone give a thumbs up sign here from these reactions, who is familiar with control theory, let's say Bode diagrams, stability. It's, yeah, thumbs down. That's all. Stability, yeah. Maybe everyone could give a thumbs up who has no idea of control theory at all. Okay, so that's at least one. And who would know how to define Lyapunov stability? Okay, maybe one. Two. Okay. So I understood this is a little more general seminar, and that's about what I anticipated. So that's quite good, because I have not prepared details about control theory. I try to share my screen here. I've tried to look at the control aspect from a little more meta level, let's say. So what's the control system about? What does it have to fulfill for tasks? What are the difficulties also maybe? And I thought, call it thoughts on controlling the magnetic levitation, because it's not like a closed proof of how to do it, which is not possible to do anyway. In my studies, I had a professor for design, mechanical design, who told us the most important thing when you want to invent something new is to look at your competitors, what's already there. And so I'll start with 2 slides of a review of the first predecessor of the Transrapid, the first maglev vehicles in modern times, let's say, outside university. And these were levitated by the company Messerschmitt Bölkow Blohm MBB near Munich. Actually, this first principal vehicle, exactly where the TUM Hyperloop team is working nowadays. The faster one 5 years later, about at an airfield in Bavaria. And so you see, in 1971, the first vehicle was levitated, and then in 76, the first time they reached high speeds. If you want to read about this more, I can recommend some publications. I wrote two on this slide here, but if you read them, you see a lot more citations of other ones. There are quite extensive publications available even nowadays where you can read how they built these systems and what difficulties they had to overcome. You see some of the most important people from that time here. The most important person in this picture is Mrs. Gottsein, who came to MBB as an IT engineer for Mr. Bölkow and then became one of the most famous German professors, the first female to be awarded the Siemens ring and known far over Germany as the mother of maglev magnetic levitation, you could say. Professor Schielen, he was my professor in Stuttgart, and he covered the university side, the academic side, you could say, of magnetic levitation. It's also in his book about vehicle dynamics. Professor Meisinger used to work for Mrs. Gottsein when she was not yet professor, but at MBB, and later went into academic field at Nuremberg. So he somehow got a connection, the link between industry and academic world. And Mr. Miller, finally, a real industry man, he was the one who made the Transrapid in Shanghai fly. And you will see some publications of these persons later on. So now what can we learn from magnetic levitation for the Hyperloop concepts that are being developed now? The first is the time range. The first principal vehicle took maybe 2 years to develop. I'm not exactly sure when they started at MBB, but somehow around this range. And then it took another 4 years to reach high speed. So no, even without propulsion, it was steam rockets here. So why did this take so long? The thing is, the first vehicle that only had 90 kilometers per hour just needed to levitate somehow, get somehow to a desired gap, while the next one, that had to control strong disturbances, get stable levitation at strong disturbances. And so this is the more difficult part to do. If you look further on, it took another 4 years until the first commercial application was happening at slow speed, and another 5 until the first passenger runs for public with high speed were conducted. You find more details about this as a presentation of Dr. Löser and Dr. Bauer, or the paper about that presentation. Unfortunately, proceedings have not yet appeared, but should appear any day now. So keep an eye open. This publication here, certainly worth reading for everyone who would want to develop a new maglev system nowadays. So this I can really recommend. Okay, so the control task. Part 1 is just about these questions. What do we have to reach concerning this strong disturbances? Then we have to say something about a magnet we want to control, because we will see that's actually a second control task. And I will say shortly something about the control systems, but not go too much into theory of control here. And lastly, say a few words about the scenarios you have to think of. So first, the primary control task. Sounds easy enough in the beginning. You have some reference line around your guide wave. For the Transrapid, this is called the central track reference line, and you want to follow that. The line is not quite correct to say, because it's a combination of 3 coordinates along the distance of the track: the vertical, the lateral position, and also the cant angle, so the torsion around this axis here. And they are defined all along the track, depending on the track location X, and you want to follow this. You also want to follow some long wave unevenness of the guideway. So the real guideway, of course, will never be built exactly as the track reference line is printed in the papers and the plans. Especially if you think of several years, buildings tend to move downwards into the ground or slide to the side or something. So you have some difference between the real track and the paper track, the center track reference line. You want to follow the long wave unevenness of this, but of course you want to ignore the short wave unevenness. Like for the Transrapid, we have girders of 25-meter length, and then comes the next girder. You have some steps in between and gap in between, or you have function models with stator packs or steel iron here, which are only 2 or 3 meters long, and then here come a next step. You don't want to follow this. So that sounds easy enough. Keeping a nearly constant gap, you could say. However, if you look at it a little more closely, then you realize it's not so easy. Because thinking of curves at high speed, for example, 600 km per hour, the maximum allowed lateral acceleration, you have a radius of 23 kilometers. Could be a vertical curve or a lateral curve. So this corresponds to about 2 millimeter change in 10 meter distance. If you think of the unevenness, now for our Transrapid especially, on our test track, we had 3 to 5 millimeter bending of these girders. So if the vehicle runs on a girder, it bends 3 to 5 millimeters and an average 4 millimeter in 12.5 meter distance. So this short wave unevenness is actually larger than the curve you want to follow. So you cannot decide by the amplitude or by the amount of your unevenness what you want to follow on what. So keeping a nearly constant gap suddenly doesn't sound so easy anymore, even to define what the control system shall do. So you have to separate these unevennesses in the frequency range. And here I've printed the power spectral density of some guideways. The blue one is our reference guideway that's according to the design principle Maglev, the published ones. And you see this spike here. So that's exactly this bending of the girdles with a 25-meter wavelength. So that's 0.04 per meter, the space frequency. So that's the double of this. The orange one is something I developed for presentation for Hyperloop once with a guideway without these single girders, but more continuously supported. This black dashed one is for a railroad. So we are about in the same range as a railroad, but it looks a bit different. So the frequency is somewhere here where you want to follow. So that's maybe 100 meters here or even longer waves. The frequency you don't want to follow a bit is this girder bending. You cannot ignore it completely because we have this 4 millimeter amplitude. You would have a 4 millimeter change in air gap. It's quite a lot. You want to follow it a little bit at least. Of course, your Hyperloop might not have this bending. Maybe it's more like the orange guideway, so you have rather 10 hertz frequency that you do not or partly want to follow. But you will always have something that you want to follow a bit in the range somewhere between 1 and 10 hertz, let's say. Also, you want to compensate some steps from if you travel from one guideway part to the next one. Let's say there's a 1 millimeter step, you want to compensate that at a distance of, let's say, 10 meters, so you have compensated it before the next one comes. That luckily is quite similar to this 5 hertz here, so no additional requirement. and you don't want to follow the shorter wavelength. So you have to consider this in your control by some filtering so that you see these amplitudes, but not this one. So that's your first control task, keeping a nearly constant gap separated in frequency range. And I now brought some official trailer of Transrapid International from 2008. You can see some of the central track reference line and also the torsion, the cant of the guideway and the curves that you want to follow. So I apologize for the sound of that use, and I hope you can. The curves is quite well distorted. By the way, if you have a question, just talk, because I probably can't see if you raise your hand here. So our first control task is, very roughly spoken, to follow up to about 5 Hertz of unevenness. So I wrote vibrations here. Better would be unevenness. Now the second thing is the system you want to control, your magnet levitation system. And if you look at the vehicle from a vehicle dynamics point of view, as you would find in a book of Professor Scheelen, you could say that a whole vehicle consists of 3 masses. One very large mass on top where all the passengers sit in, the car body. Then a smaller mass, which is the connection between the magnets. We call it the levitation chassis at the Transrapid, and then the magnets on it, separated by springs. And of course, the magnet has an electromagnetic system that we need to control. So what we give is a voltage to the magnet, then some current follows from this, and from the current follows a force, and finally we move the mechanics. You all know that for the electromagnetic suspension system we are talking about here, this is inherently unstable. So we have to stabilize it. But before we can do it, even before we can stabilize it, we somehow have to get a current into the magnet here. We can only apply a voltage at the ends of the electric line and need to get a current. And I would talk about this in this second topic. I said I won't go too much into control theory, but I have to show a few equations from the magnets. And I hope you're a little more familiar even with magnets than with the control theory, being Hyperloop engineers. So if we look at a magnet in a very simplified way with the typical U-shaped magnet here, we have this force equation, which is also sometimes called the Maxwell equation for the magnetic force. depending on the area you have here, on the flux density and the constant mu0. And you have to get this flux through the ion. The green part is the ion now here. And all these ions have the saturation property. You certainly know. I've just curved for one ion here, a typical ion for magnet applications, but other ions look pretty similar. So we want to use the ion, so get a high magnetic inductance B. It's drawn here via the magnetic field. The magnetic field you achieve by getting the current in there. It's about proportional to the current. And of course, we don't want to have very high current for just a little more inductance. So we want to be somewhere here. So we get a high force, but not too much in the saturation. So your operating range typically is somewhere around 1 Tesla. You might go for 1.2, 1.3 maybe, but then you're already quite in saturation here. And for an example, we can assume you are somewhere here. And you see from the magnetic equation, if you have chosen this magnetic flux density here, then you have a direct relation between magnet force and area. So you can immediately say, what area do you need to carry, for example, 10 kilonewton, about 1 ton of your vehicle? This about 25 centimeter to 10 centimeter, divided with these two areas here. And it's not really dependent on how your magnet shape actually looks. It's just this relation. And if you further now choose the gap you want to aim at, you already know your magnetic resistance and you know your, I call it the magnetic voltage. It's also called the magnetomotive force sometimes. So the number of windings times the current. You have 16 kiloampere for 2 air gaps, so 8 per air gap. And this is not depending on very much geometry. So all of you will be somewhere close to this. In fact, you can reformulate the equations here so that you see this n times I, this product, is only dependent on this B, the magnetic flux density you have chosen, and the air gap, not even on the area. So if you want to have double the force, you can double the area, so make this longer, but you still are at the 8 kiloamperes per air gap. So I guess all of you will be somewhere in different, in a similar range here, unless you use permanent magnets or superconducting magnets. And now we are at a point where we can choose as the first time as an engineer between the number of windings and the current you want to have. I just have one example here, but of course you can choose 300 windings and 50 ampere or such like. This 30 ampere is a sensible range for typical electronic components, transistors and so on. So it shows that. And from this follows your inductivity. Here it's 0.2 Tesla, and that means it takes more than 0.1 seconds to get the current running once you have your voltage in there. Or half a second until you are where you want to be with your current if you apply a step of the voltage here. Let's say you say the voltage to the level you want to be in the end, you need to wait half a second. So that's of course too slow if you want to control your magnet at these 5 Hertz we talked about in the control task 1. So we have to speed this up. You can do this, of course, by applying much higher voltage here in the beginning, let's say up to here. Then your current will get up much faster, and then when it's here, then you put your voltage down again to that level where you want to reach. But that's a control task you have to do in addition to all the other control. So that's your second control task, speeding up the magnet current. And I have another part of that official trailer where you see how the magnets in the Transrapid look like. So that's our stator. The green part is iron laminated. Here comes the levitation magnet with 12 poles, 12 coils. They are controlled by two control units, one for the first 6, one for the other 6. Here are already the gap sensors. So we have 2 gap sensors per each control circuit for redundancy. And now come the guidance magnets with a little different geometry. And this we call a magnet module. And we have several of them along the vehicle. Now another important thing here, we have placed all the electronics in such boxes that you can simply slide in. They are automatically connected at the end by some plug and connection system. So you just have to push them in and lock them and unlock them with these grip handles here and pull them out. So you can very easily exchange them. If during a ride you see one of them fails, you can exchange them in a few minutes in the maintenance. So that is the magnet system we have to control. That's our second task, to speed up the magnet from about 1 Hertz in this example here. Of course, you may have a dynamic of your inductivity of maybe 2 Hertz or also half a Hertz, let's say. Transrapid, we are a bit slower because we have large magnets. And you have to speed them up so that you can control the 5 Hertz vibration. Now, some words about a classical control system to do that. So the first thing is, if you look at this mechanical setup, that we decouple the large mass up here from our magnets down here. So with this 5 Hertz, we only have to move the magnets and not the large mass up here. Besides, passengers do not want to be moved by 5 Hertz. So our control system only needs to control one corner of this levitation chassis here. And this actually is called the magnetic wheel. That term was invented by Professor Gottsine. So that's one part of a magnet controlling the force in one corner of our levitation chassis and these decoupling springs here. So that expression shows it quite vividly what is done. We have only to look at one magnet and don't consider all the rest of the vehicle. Just like one wheel at a car rolls along the road and vibrates maybe, jumps a little around the road without caring for the rest of the car. And then the car just stands on soft springs on these 4 wheels. And we don't have a control system from the car right to the rubber of the tire of a car. And so we also have to consider only control of one little part, one magnet, so one magnet controlling one magnet part, without having any effect of all the other magnets in the system to consider. The typical layout then, as it's written in the famous paper about the magnetic wheel, is a state control system, full state control, combined with a Kalman filter for the observation. So we measure the air gap, we measure the acceleration here, and then we have some calculation scheme that calculates all the states. So the Z position of the magnet, Z dot, the change of the gap, and so on, the flux even in here. It's all calculated from these sensors of gap and acceleration and current. I don't want to explain this in more detail than here, but if you are interested, you can read the famous paper here of Mr. Gottsine, Mr. Miller, and Mr. Meisinger. I am happily in the possession of an original that Professor Meisinger gave me, but you find the PDF somewhere. So what I want to talk about is the speed that your control system has to fulfill, because you might set it up a little different than in this old paper, although it would still be possible. Transrapid is not so much different from that system published in the paper. But however you set it up, you have to consider these speeds here. The first is if we want to control something around 5 Hertz, that means our time constant of the system is smaller 30 milliseconds. So time constant means if you switch on some desired gap, it must take less than 30 milliseconds until your system reaches that, or at least the magnetic force reaches that. Then secondly, so that was our first control task, yeah, coming from the unevenness. So secondly, we have to speed up the magnet. And in our example here, we said we have 120 milliseconds until the current is where we want it to have. So that corresponds about 1.3 Hertz. So that's about 4 times too slow. So let's speed this up by a factor of 4. So we have about a period length of 30 milliseconds instead of 120. And yeah, now I have to say, we said we want to get the voltage very high until the current reaches what we want, then set the voltage down. So that's a whole period of the voltage. And so this whole period is about 30 milliseconds then, if we have sped up by a factor of 4. And so if the period is 30 milliseconds, it means the time constant for our voltage setting is a smaller 5 milliseconds. So if we want to control something with a time constant of 5 milliseconds, our hardware of the control system, our digital hardware, digital clock, needs to be somewhere in the range of 1 millisecond, maybe even better, half a millisecond. So this is some requirement to control your control system where you do not have to consider very many details of your setup. It just follows from the general control task. Secondly, I have to say something about stability now, as we are talking about control engineering, but I will not show equations and just mention that what you typically talk about in control theory is something which is called a Lyapunov type of stability. This is for every control system necessary to fulfill. In easy words, it means that a system works at all. If this is not given, the system doesn't work at all. So you always look at this in control theory. But in our case, this is not enough. In your lectures about control theory, you will often stop here. If you have managed to give to parameterize your control system such that Lyapunov stability is given, then for most systems you can stop and say your goal is reached, but not here. We need stability against these periodic disturbances of the guideway, because we do not only have accidental random disturbances. Your guideway always have some repeating things coming. In our case, this 25-meter girder length. Some girders are longer, others shorter, but somewhere around this. You have your segments of your tunnel, which have a certain length. You have mounting points with certain distances. So you have repeating disturbances. And this is not covered by the typical control system theory. So you have to look how your nonlinear system copes with these repeating disturbances. And this under limits. You don't have unlimited voltage. You have just your onboard voltage that you can use. Current, you can never have a negative current. Current 0 is the smallest we can do. Doesn't make sense to give a negative current because then you have a pulling force again. Your gap has a limit. It can never reach too close to 0 or you collide. So you have to respect these limits and still get smooth levitation, as I called it here. Could call it some kind of stability. And both of these conditions you have to fulfill under varying parameters. Varying load, aerodynamics, some tolerances, stochastic unevenness, and so on. So that's what engineers typically would call stable levitation. Although if you have a control engineer in your round, they will disagree and say stability is clearly mathematically defined, and it's this one here. So there's also a lot of discussion if you have control engineers and non-control engineers talking about stability. But after my experience, most engineers call this a stable levitation only if all this is fulfilled here. And if you have managed to set up your control system to give the voltage to your system in that way, then you can follow your centric reference line, somewhat the unevenness, but not all unevenness, as we desired and as it's indicated in this animation here. This animation now is from a simulation, but if you look at measurement results from our test track, it looks very similar to that one. Of course, that's exaggerated a lot here, a factor of 10 or so, but you can recognize quite well that we do not follow everything of the guideway, but some parts and the unevenness in some way. Here you see the currents, by the way. You see how the currents have to react very fast, although your passengers should not move fast. So much about a classical control and the term stable levitation, maybe. Lastly, a few thoughts on the situations you have to consider additionally. So the first one is the nominal situation. So that's our control task 1 and 2, which we fulfill by the classical control. Secondly, you have to control your start of levitation and settling down. This might seem very similar, but usually you have a much larger gap here because all the elasticities in your system needs to be coped before anything lifts off. For the Transrapid, for example, we have here this 10 millimeter nominal gap, but if we settle down on our skids, we have a 30 or 40 millimeter gap. And for the first 10 millimeters of magnet moving up, nothing happens up at the vehicle, it's still on the skids. So here it's a completely different trajectory. Secondly, you might have to have the start of levitation even during your ride. If for some failure scenario, your control system has switched off, or failure detection system has switched your control unit off, you might want to restart it so you don't have to drive for the next 300 kilometers without this control unit. At least try a reboot. And so you have to lift off at very high speed, possibly unknown speed. Then if that is not successful and the control unit really fails for the rest of your ride, the other control units have to take that load over. So you have to have some communication and you have to have a control system that not only works in a nominal situation, but also if another control unit has failed and you have completely different loading situation. Lastly, you might have some unusual loading. Of course, you should consider all possible loadings in a nominal situation here, but I put it as a 0.5 here because you probably won't consider this in your first prototypes and for the first runs. But that's the reason why it takes another years until you have commercial operation. There are such strange cases as all people suddenly running in one part of your vehicle. Now for the Transrapid, we have trains with several sections. there's a case to consider that there's maybe a little fire in one section or some other reason why people panic, and we have to think all of them run into the neighbor section, into the neighbor car. Suddenly you have twice as many persons in your car as thought, and you don't want to have a follow failure by your levitation settling down then. You, of course, usually only have one pod, but even here, something may happen at one side of the pod that people panic and all run to one side of the pod, pressed together in one side of the pod. So that magnets in that corner suddenly have twice the load. And you have completely different point of center of gravitation and so on. So I put this as 0.5. And now I would call this a robust levitation and guidance. Everything I said here, you can concerns guidance as well as levitation. Guidance really is very similar. I would call this a robust levitation if you have this, what we in practical language call stable levitation before, but not only for case 1, but at least these 5 scenarios. You might find even some more scenarios if we think about it. So that's my own definition, I have to say, because robust stability and control engineering, again, is very clearly mathematical. It's something a little different, similar but a little different to here. So this is, I call this robust levitation, not robust stability of a control loop or something. Now, I won't go through everything on this slide in detail, just want to mention there is a method of systems engineering, how you can find these 5 scenarios I've just talked about. Because if you think about these 5 points and what could happen in your system that fits to one of these 5 scenarios, there's quite an unoverviewable number of scenarios you can think of. And systems engineering has some very systematic methods of finding all of these scenarios, not forgetting anyone, with reliability, availability, maintainability, and safety to consider one after the other. Right. And I just want to stress availability is what it all boils down to in the end, once safety, of course, is fulfilled. And this really makes the difference between a system just for demonstration and commercial applicability. You see this at German Rail at the moment. They have nice ICE trains running 300 kilometers per hour, which is not so bad for most distances. But now if you have a ticket, you have to plan that it takes maybe 1 or 2 hours more. So that's not at all the same system. And the reason is that at the moment, at least German Rail does not have a good availability. If you have a good availability, that means even if things fail, your passengers are still traveling on the planned timetable. Then you get something like our system in Shanghai. And allow me to show one more advertisement video from 2008 about that system. So if you have that availability, then you can also reach a punctuality that your passengers will like. And that's my last slide. Very roughly summed up everything here, although the whole thing is a summary. We have to follow some unevenness of the guideway, let's say somewhere below 10 Hertz. Above that, you want to ignore, and you have to follow everything under maybe 1 Hertz really directly. So that's your central track reference line. For doing that, you have to speed up your electromagnetic system first. So that's really a second control task your system has to fulfill. Then we can reach the stable levitation and guidance for this originally unstable system. And lastly, this is not enough if you want to have a successful commercial application. You need what I call robust levitation and guidance. So have this stable levitation at all possible scenarios and have your vehicle running with timetable speed, even if some components fail, and even without having to take the train out of operation once it's at the next station. Just continue for the rest of the day without the passengers realizing anything has failed. So thank you once again for that opportunity here to talk. Now I'm open for questions, of course.
Lukas, are you taking over the questions? Should I? Ah, okay.
Ich weiß nicht, wie man mich verstehen kann oder ob ich so
We
abgehackt
can
bin,
hear
wie
you.
ich.
We can hear. We just
Okay.
need you to stay with English, but yes, we can hear.
Okay. Oh, sorry. Perfect. Yeah. Sorry, my audio was somehow disrupted, and I didn't know if you can hear me. But of course, if that's fine, then I can do the questions. There's 4 questions already, and then we can. I see that the watch party that we have from Heart also has a few questions probably. So let's start with the first one. The first one is quite easy. How much banking is in the Transrapid in Shanghai, and how much is in the test track in Germany?
Oh, good question. I know the allowed limit according to the design principles is 12 degree. And on the test track and the TVE, we certainly had that 12 degree. I'm not exactly sure whether we have that 12 degree in Shanghai really fully used, but could be.
Yeah. Then there's a second question. Where does the 10 Hertz frequency arise from that you calculated in your graph that we've shown in the Hyperloop reference trail?
Oh, that
reference track, I think.
peak in the orange one.
Yeah, because you said the 5 Hertz was from the pillars, basically from pillar distance.
Yeah, so you mean this peak here, right?
Yes, that one.
Yeah. Yeah, well, I let's say I built some example guideway in our simulation software, and I assumed that you do not have every 25 meter a pillar as you are in the tunnel, but you will have some functional modules that are set up at a certain repeating distance. And here I took a distance of 9 meters because the company Max Bögel has built such small girders on the test track in Emsland and tested successfully. So that 9 meter was a length that they could easily manufacture in their factory. So that could be that it's easy to get such concrete parts of 9 meter length. And then you have some periodicity with 9 meter wavelength, and that's this one here. But that's only a guess of me, of course. If you build your guide very differently, it will have some repeating disturbance, certainly, but probably at another frequency.
Okay, that's just a perfect question. That's following that up. Do you think that repeating structures in the tube need to be avoided because of the maybe aerodynamically induced periodic disturbance that creates to a vehicle, for example?
Well, maybe I can stop this here so we can see each other better. In principle, of course, it's good if you have as little unevenness as possible and as little repeating unevenness, especially. So if you're in a tunnel, you have, of course, a much better chance than if you're up here on some girders above the land. And I would very much recommend to use that. I think it's not perfectly to be avoided. You will have some repeating sequence unless you build every part of your guideway differently. And you want to have something coming out of the factory at reasonable costs, so that will always have the same length, and you have fixations on your guideway. You could try to play around with that to have not at the same intervals your fixations, but maybe changing intervals. It's something we do at our magnet poles, actually. There we don't have the magnet poles all in exactly the right periodicity, so to speak. But you will have some repeating things, certainly.
Okay. Then there's more questions. Again, if you want to ask your question yourself, feel free to speak up. But otherwise, I'll just start asking the next question. There's a question that says, can you shed some light on the method employed to achieve robust levitation and guidance?
Sorry again, the method of what?
The method of employing robust, or the method employed that you employed to achieve robust levitation and guidance.
Ah, okay. Yeah, that's exactly the thing about the robustness. Yeah. So as this question is formulated, I guess it is meant robustness according to control theory. And that would be defined in a way that you have Lyapunov stability. So now I have to say for the rest here what that is. It means if you have some disturbance, so at one point in time you are not at your desired location, then you can calculate that your system will get you back to this desired point in some finite time. And it might be any disturbance, and you will always come back. But this definition assumes that during that time there's no other disturbance. So that's not enough for us here. Now, this robustness in the control theory sense would be that this Lyapunov type stability you have even for different loading conditions, for different tolerances of your, let's say, your electric resistance or so on. And there are clever mathematical methods that calculate a whole field. We haven't done that because it wouldn't help much, because we do not have such a linear system with infinite current, infinite voltage, and so on. And we don't have time until this gets back to the desired value. We really have to consider that we have limits to the control quantities, to everything, to even to the gap that we may have. And the next disturbance comes very quickly after the first one. So there's no mathematical closed solution to that. So what we do is we use the standard linear control theory to get some sensible parameter set for a simplified linearized system. And then we do simulations with worst cases and with many stochastic cases. And from this, we can somehow cover most of the range, let's say. It's not a mathematical proof we can have for this robust levitation, which I said here. Especially robust in my sense is also for all the failure scenarios and tests. So in that time that the Transrapid was built, none of that was done, of course. The computers were not fast enough for that. So this was done by practical tests. That's why this test track was built. Most of it was just proven by traveling millions of kilometers and nothing has happened. For nowadays standards, that would not be enough. And in fact, we are somewhat busy at Transrapid also with new control systems and developments. And if we want to prove according to nowadays standards, it's a difficult task. And as I said, there's no mathematical closed proof. You have to have some method combination with what you can prove mathematically, with test benches where you can set all worst case situations or many worst case situations, and then first tests on the test track. And talking with the authorities who have to sign in the end so that you know what's important for them. Start that early in your process.
That's some very good advice. Any follow-up questions on that? Otherwise, we'll go over to the next one. Doesn't seem like it. Okay, let's go for the next one. The next one says, how did the performance differ on the Transrapid between any concrete or steel girders? Sorry.
Yeah. We started with steel girders. So the first part of the test track is built from steel girders, the second from concrete. That was planned right from the beginning to have the comparison between both, because there were different theories. Some people even say the steel girders was the reason that thyssenkrupp started in this, or Thyssen Technologies at that time, because they wanted to sell their Thyssen steel. I'm not sure whether that's true, but they built the steel girders, and the concrete girders proved better in many ways because they have more damping. So with the steel girders, the problem is that not the vehicle has some problem with follow the unevenness or starting to vibrate or having this stable levitation, but the guideway starts to vibrate and make noise. It's not large vibrations, of course, you won't see them, but you hear them.
Yeah.
And they tried some damping measures in the test track here. In the end, they filled stones inside the steel girders, so to damp them a bit. But the concrete girders are very well damped right from the start. So that's why for
basically a lot
Shanghai
about
we
mass.
only used concrete girders.
Is it in essence also from the mass of the concrete?
I think the mass was pretty similar in the end, at least when the stones were filled in.
Yeah.
But the concrete has inherent damping and the steel has nearly no damping.
Yeah, this is also something we see in our pipe.
Or here.
Or here, indeed, that we have these couple of vibrations.
So a question on that. So you mentioned that there was this frequency in the steel girders. Was it a fixed eigenfrequency, or would it also vary depending on the load case?
Yeah, now were the eigenfrequencies of the girder that were excited by the system.
Would it be possible? So one thing here at our small test facility, we also have some eigenfrequencies of the facility and some patch to fix it temporarily is to just notch filter these frequencies away, and it helps quite well for now. So I wondered if this also was something that was tried back then.
For our cases, this could not work. If you mean filtering away the frequencies in your control loop, right?
Yeah, exactly.
Yeah. So if this helps in your case, then it's not so bad as with these girders here. Now maybe, yeah, I would assume that your tube is a lot more rigid than these girders here. Yeah. The thing here with these girders is, if you keep your current constant in your magnet, then and your magnet stays where it should be, but the girder vibrates, so it gets closer, the force gets higher. So just the vibration system of your girder itself is an unstable system. If you have a magnet in one fixed position with a fixed current. So even if we ignore the vibration of the girder in our control loop, it's still for the girder an unstable system, even if we ignore it to 100%. So what we could try is to control the motion of the girder, not only of the magnet, but also of the girder. So we have two moving systems that we would control. Sounds incredibly difficult to me, but it, theoretically you could try to control the girder movement at frequencies of, let's say, 30 hertz or 50 hertz, and the magnet motion at frequencies below 10 hertz. But then it means that you have to change your current in your magnet by 50 hertz. And you saw in our system, it's difficult to change it at 10 hertz even now. So if it helps in your system, I would say that it's a different scenario, a different situation that you had that you could hear.
Yeah, we see this eigenmode at around 70 hertz. So there it helps.
Yeah, so we just ensure that control output does not excite this eigenmode. It is 70 hertz just by applying a notch filter on the input of the gap. So yeah, doesn't excite.
Yeah. So that was the problem of the control loop then before, yeah.